Welcome back, ladies and gentlemen. Here we are with the solutions unit. This one should be a continuation of our basic study of physical properties of matter. We're going to be looking more into liquids, right? We've done solids in physical properties itself, then we touched on gases and we got into gases. Now we're going to be investigating liquids and their general behavior. And what we're going to see is that the behavior of liquids is very, well, straightforward in a lot of ways. Although, like usual, there's details that we're going to have to account for, things we're going to have to understand and learn. Nothing too fancy, though. All right, let's get into it. First things first, remember when we did this? We classified matter, right? And we said that there were mixtures and pure substances. We spent a lot of time dealing with pure substances over the last little while, right? Elements and compounds. We've dealt now with ionic compounds, covalent compounds, organic compounds, all sorts of different things. But now we're sliding into the mixture side of this equation. We're going to be looking at heterogeneous and homogeneous mixtures. Remember, these are what they are, right? A homogeneous mixture, everything is mixed together very evenly. A heterogeneous mixture, you've got clear differences. There's this area and this area. That's kind of it, but let's look at it in more detail. Mixtures can be either heterogeneous or homogeneous. The particles in a heterogeneous mixture are not evenly distributed, and individual particles are often distinguishable. So salt and pepper, right? If you have salt and pepper and you put it in your hands, you can clearly tell which one are pepper and which one are salt because the salt will be white and the pepper will be black. The particles of a homogeneous mixture are evenly distributed and cannot be easily distinguished, right? So if I take some sugar and I put it in water, and then I take my glass of sugar water and I look at it, I can't see the sugar most of the time. There is like one little exception, well, we'll see that a little later on. So a pure substance versus a mixture, really the difference is just if the pieces are bonded together, right? Like in both of these examples, there's the same number of pieces, but here they're connected and here they're not. That's kind of it. So let's look at a heterogeneous mixture a little more. A heterogeneous mixture, hetero in this case meaning that they are like distinct or separate, will settle out if left to stand. So if I have a glass of a heterogeneous mixture and I just leave it on the counter sitting there, eventually the two different materials will be in two separate layers. There are two main types of heterogeneous mixtures as a result. There is what is called a suspension, where very large particles are sort of floating in a medium of some form. The components can thus be separated by some kind of filter. Example, oil and water. If we shake it, it will temporarily mix, but then it will separate over time. The other type of heterogeneous mixture is called a colloid. A colloid has small particles, not big ones. So because the colloid has smaller particles, it will behave a little bit differently than the suspension. So a colloid will have a cloudy or milky appearance. You won't be able to see through it because of its, sort of foggy character. The particles are going to be evenly distributed throughout the medium, so there isn't going to be distinct layers as much, right? Like with water and oil, you get water here, you get oil here, because oil is lighter, so it floats on top. Water is heavier, so it sinks at the bottom. But in the case of a colloid, you're going to get things that are more evenly distributed, but if you were to zoom in, you'd see, oh yeah, this is clearly different than that. It's just that to, a casual inspection, they might look the same. Glue, whipped cream, paint, gels, emulsions, foams, aerosols. Honestly, the biggest example here is milk. Milk is a colloid. Milk has water as the bulk of it. That's why it's a liquid. And then the rest of it is fat. A couple proteins, a few vitamins, but mostly fat. That milk fat is what you can then use to make other things like clarified butter and ghee and other stuff. But the key thing is that it's still a colloid of a combination of things. The higher the percentage of milk, right? So like you get 0% milk, then 1% milk, then 2% milk, whole milk, home. Either way, you can tell which one I don't drink. Either way, each one of them is telling you the percentage of milk fat in the particular colloid. So 0% skim milk has almost no fat at all, right? It's 0. 1% has very little. 2% doesn't have much either. The reason why different types of percentages will taste differently is because of how much of the fat there is. And as we discussed, fat is a useful thing, but not the only thing. And, you know, the more fat, the more calories, problem. Okay, what about a homogeneous mixture? This one's going to be the more difficult one and the more important one for what we're going to do. A homogeneous means uniform, means they are the same. So uniform throughout a sample, such that every part of the material is exactly the same as any other part in terms of appearance and phase. So basically, if I sort of reach in and scoop it out, I won't be able to tell the difference. I'll get a random arrangement of particles, and they'll all be kind of a mix in some way, but they'll all be basically the same. So a solution, this is a key word here. This is like the solutions unit. Here's solutions. A solution is a homogeneous mixture that may be a solid, a liquid, or a gas. And it is composed of a solvent and a solute. Yes, those two words are almost the same because, as we've discussed before, chemists are bad at naming things. And so once again, they named things badly. So a sol, it's got sol in the front because it's a solution, right? There's that sol covered up. There's sol. Then there is a solute. And over here, we've got a solvent. Vent. So what is each one? What do they mean? Okay, let's see if we can explain it. Solutions have two parts. Okay, the solvent is the dissolving medium. In this case, medium does not mean halfway between small and large. Medium in this case means like the material or the stuff. So, for example, the medium by which you are hearing me right now is through a video. That video is the medium for my message. Normally, in a classroom, the medium would be the air by which the sound of my voice would flow through. Right? Without air, can't hear me. Underwater, the medium would be water because the sounds, the animals, they move through the water. Right? So a medium is just a material or a group of things in a way. Anyway, the dissolving medium is usually the substance present in the greatest amount in the solution. So, for example, right now I'm in a room, there's a lot of air in here. Like a lot of air, because I'm not suffocating. So that, we could say, would be the solvent. Now, solute is the thing that is dissolved in the solution. And it is usually the substance that is in the lesser quantity. So a mixture, remember, is when we take two different things and we put them together. So the question becomes, how do we distinguish them? How do we break them down? And the chemists wanted another binary category because they liked those. So what did they do? They said, okay, the one that there's more of, we'll say is the medium, and the one there's less of is what's dissolved in the medium. Okay? So in the case of the air in the room right now, there's lots of air in here. There's some water in the air, right? There's humidity. So that humidity, that water, is dissolved into the air. Yes, air can be a solution. Actually, as we said on the previous slide, anything can be a solution, a solid, liquid, or a gas. Any mixture of those can be a solution. I can have a solid, I can have a liquid, I can have a gas, liquid. There's so many options, which is important because it means we're alive. So here's a picture of it, right? The solvent, in this case, is water, and the solute is something I'm putting into the water. Right, so sugar in water, for example, or the soda pop syrup put in water, those would be examples. So consider making a lemonade, right? You mix the lemonade crystals into a glass of water. I'm assuming you're making packaged lemonade, not fresh lemonade with actual lemons, but if you had a packaged powdered drink mix, you would take that, put it in the water. The lemonade crystals are the solute because there's less of them, and then the water is the solvent because it's more of it. Now, you may have noticed, right? I could always flip this around. I could take, for example, the tub of lemonade, right? And I could just pour a little bit of water in to make it like slightly damp. That would be the reverse solution, right? I'd have more lemonade powder than I would have water. So in that case, the powder would be the solvent and the water would be the solute. Would that normally happen? No, not really. I guess unless the seal was broken and some water got in. Nobody would ever want that. Usually we want to have more water than drink crystals. Depending on, who's making such powdered drink in your home, your parents will probably put very little drink crystal in and a lot of water, because then it extends the life of this thing, goes for a long time. Kids always hate that. They're like, no, put more, I want more flavor, right? All right. What are some characteristics of a solution? I wanted to say solvent again. What's the characteristics of a solution? First, they're homogeneous. Well, that makes sense. I said these were the homogeneous type. So yeah, okay, the homogeneous type are solutions. Solutions are homogeneous. That's not a big surprise. They look the same throughout. So when I scoop in and I grab a bunch, any bunch that I grab will have the same properties, right? So I reach in and I grab some. Yep, all right, that looks the same as this stuff. So there's no real difference between any amount of sample that I take. The solution is stable. This is a big difference between a homogeneous and a heterogeneous mixture. A homogeneous mixture is stable. If I leave that soda pop on the counter, it will not separate into the individual pieces that it was originally made from, right? There's water in there. There's the carbonation, which is carbon dioxide, as we're going to see in more detail. There's the syrup, which is made up of a variety of sugars and flavors and food colorings and other things. Fun fact, Coca-Cola, it's actually lime green if they don't put in the dye to make it look brown. So all of these things will stay stable. I can take that can of Coke out and it can be years old and I can open it up and it'll be just as good. This stability is important for a lot of things, and that's how we know that solutions are unique, or at least important, significant, we'll say. Both the solute and the solvent pass through a filter if you try to filter it. Basically, we can't make a filter small enough to separate a solution. And the answer is like, wait, why not? Well, think about it, right? Here we go. Here is our filter. You can literally see through this, right? If I try to put markers through it, it doesn't work because the marker is bigger than the holes. If I try to put this paper clip through, it'll fit, right? I can put it inside because it is smaller than the holes. That's the basic idea how a filter works. So the problem is that in order to separate a solution, we would need a filter the size of atoms, or at least molecules. We don't have such a thing because we can't make something so small that it's only atom big. At least, not yet. Maybe we will in the future. But right now we can't. So once you've made a solution, you have no way to separate it, at least no physical way, right? We can't filter it separate. And there are a few other tricks for how to separate a solution, but they're tricky. I said there were 5 things. There's the first 3. Number 4. Solvents and solutes may be gases, liquids, or solids. I said that. I said they could be anything. And they can be any combination of them, right? Normally, when we're talking about solutions, we're mostly going to talk about putting solids into liquids. Like 99% of the time, that's what we're going to talk about. But I could put a gas into a liquid. I could put a liquid into a gas. I could put a solid into a gas. All of these, you think like, well, when would that ever happen? When we go through some examples, you're going to be like, oh, actually, that happens all the time. Now, the reason for that, of course, happens to do with the fact that, again, this is a category that we've invented. So it's going to apply in a lot of situations because we made the category, so it will work because that's how we want it to work. Sometimes it's more useful than others, though. Finally, number 5, solutions are considered to be a single phase, even though the components may have been different phases before the solution was formed. And we've always kind of known this because way back in the distant past of grade 10, we talked about the fact that a chemical can be in 4 different phases. We said that there were solids, we said there was liquids, we said there was gases, and we said there was aqueous. And at the time, I would tell you guys that aqueous meant dissolved in water, aka a solution. Ta-da! So aqueous is sort of considered, or, solution is considered its own category, which, why? Because it's pretty critical. It's pretty critical. We're going to see that solutions play a major role in chemistry, biochemistry, any number of things. The reason we're alive, solutions are involved. The reason we can do any chemistry at all, solutions are involved. Now, types of solutions. There are three common states of matter: solid, liquid, gas. We're not going to talk about plasmas here because there's not really any plasmas on Earth, so we're just going to stick with those three. Therefore, there are 9 possible combinations of solvent-solute pairs. 9 possible combinations. So there are 9 types of solutions. And under normal circumstances, this would mean that there would be 9 distinct individual names for every single kind of solution. Because chemists are bad at naming things, and they always make things more complicated than they need to. I have good news. This time they didn't. They just called them exactly what the combination is. For example, the solid-liquid solution. The liquid-liquid solution. Very straightforward. Very straightforward. Finally, I mean, the names are still bad, but at least they're straightforward. They didn't use another language or anything, nothing fancy. So let's do some examples. Solute of a solid, solvent of a liquid. These are going to be some pretty standard ones. You're going to be finding them very familiar. You're going to be like, oh, okay, yeah, I know that. I know what that is. No problem. So what do we got? First example, sugar and water. Very easy, right? Remember, solute means it is dissolved into the solvent, right? So there's lots of this one. There's very little of this one. So sugar and water. What's some other examples? Salt in water. It's a very good example. Iodine in alcohol. Probably not a good example. What would that be for? Disinfectant. Iodine is a disinfectant. Alcohol is a disinfectant. You put the two together, you can splash a little iodine alcohol solution on a cut in order to disinfect it. Hurts like crazy. Stings. Oh, my word, does it sting. But better than dying. So, I'll take it. Liquid-liquid. This is going to be a little bit trickier. We've already got a couple here, right? Methanol and ethanol for industrial alcohol. Now, as we're going to talk about in the organic chemistry unit, methanol and ethanol are both alcohols. Alcohols are all toxic. They're all poisonous, but some of them are instantly poisonous, and one of them is poisonous slowly. Ethanol is the slow poison. That's the one that humans decide to drink every once in a while, at least some humans. Methanol is very quickly poisonous. That one will make you go blind and then have nerve damage and then stop breathing and die. Yeah, I know. So here's the thing. Alcohol is useful for a lot of organic chemistry, for a lot of industrial processes. But if you leave a bunch of ethanol lying around in a factory, it's possible that some people might decide to borrow some for personal distillation purposes. This is an issue if you're a company. So what do? You put a little bit of methanol in the ethanol. Not a lot, just a little bit. But it means if anyone walks off with your starting chemicals for your factory, they end up in the hospital. Then you can fire them because you knew why they got it. Also, they'll be super sick and maybe dead. So, yeah, industrial alcohol has other types of alcohol added to it just to make sure nobody drinks it. Ethylene glycol in water makes engine antifreeze, and then we've got one here that is talking about gas line antifreeze, methanol in water. So once again, these are all solutions of two liquids mixed together. And when you actually first mix the two solutions together, you can kind of see it. Like you've done food coloring in water. That's another liquid-liquid solution. When you put the food coloring in water, you can see the food coloring slowly swirl and then mix, and then eventually it's fully mixed in solution, and it doesn't move anymore. It's homogeneous at that point. The same thing will happen with almost any of these as well. When you first put them together, you can tell, but not for long. All right, let's do some other crazy ones. Gas and liquid. Okay, so gas in a liquid. Gas in a liquid. The one that's uncovered so far. Dissolved oxygen in water to support aquatic life. This usually surprises people who don't have fish for pets. Fish, animals that live in the water, breathe oxygen, just like us. The difference is how they extract the oxygen. We have lungs, which are designed to separate oxygen from carbon dioxide, nitrogen, and argon, and a few other gases in the atmosphere. Fish do not breathe air. They breathe water. When they breathe water, they have to extract oxygen from the water. So they have gills, whereas we have lungs. They do the same basic job, extract oxygen, but they do it through different methods. Now, why is this kind of critical? Well, a friend of mine, this was quite a few years ago now, they were so confused because they had fish and they wanted to clean their fish tank. And they took the fish out of the fish tank and they put them in a bucket. And then they cleaned out the fish tank, but they forgot something. So they had to go to the store, and then they came back, and when they came back, all the fish were on the floor around the bucket. They had jumped out of the bucket and, well, died on the ground because they can't breathe air. Their gills don't work in the air, just like our lungs don't work in the water. And they were so confused. They're like, why would the fish jump to their deaths? Another friend of mine who was very big into fish and chemistry was like, well, so there's a problem, you see. Water doesn't have infinite oxygen. It has a certain amount of oxygen, and over time it will lose it because the fish will use it up, and it will replace the water, the oxygen, with carbon dioxide, just like any old animal. But you see, a bucket of water, there isn't a lot of oxygen being added in. From where? From plants. Well, there's no plants inside of a bucket. Underwater plants also add oxygen because that's what they do, right? They take in carbon dioxide, they add oxygen. They breathe out oxygen. There we go. Well, there's no plants in a bucket. So the other way to get oxygen in is for oxygen to dissolve into the liquid, making a solution from the air. So it comes in. Well, the bucket doesn't have a lot of movement on the surface. So there's not a lot of oxygen coming in. That's what those little bubblers are for inside of a fish tank, right? There's a little like thing that usually sits just on the edge of the fish tank, and it bubbles away, bubble, 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 bubble. What its job is to like help push oxygen into the fish tank to make sure that the fish will have enough oxygen. So those fish jumped out of the bucket because the water in the bucket had no oxygen left. So they had two choices: stay in the bucket and suffocate because they had no oxygen, or jump out of the bucket and hope they could find another source of water before they suffocated. Turns out there wasn't any, so all the fish were gone. So that's a weird one. What are some other examples of gases in liquid? Carbon dioxide in water in order to make carbonated beverages. The bubbles from soft drinks is made from carbon dioxide. The addition of the carbon dioxide is what gives it that bubbly character. So we put extra carbon dioxide in the water, and it bubbles and fizzes. Okay, solid in solid? Huh? Solid in solid. Look at some of the examples here. 14 karat gold is 14 parts gold and 10 parts other metal. 14 karat gold, 8 karat gold, 10 karat gold. What this tells you is the ratio of solvent to solute. Why would we make a mixture of gold and other metals? Gold itself is A, expensive, and B, fragile. It will melt in your hand. Yeah. Gold has a melting temperature that is so low that if you were to hold gold in your hand for long enough, it would start to soften. Well, jewelry that starts to soften isn't very useful, right? Because you're wearing the jewelry and then it like gets all wobbly and falls off. That's not helpful. So what you do is you mix the gold with a bit of other metal, like say nickel or steel, iron, whatever. That way the gold ring or necklace or whatever becomes stronger, but it's also cheaper because you don't have to put as much gold in it, right? So you get to make twice as many pieces of jewelry. It's very convenient. There are some others here, right? Let's take a look at some of these. First one on the list, zinc in copper makes brass. And if you do copper in tin, you make bronze. These are types of metals that are very useful. You mix the two metals and you get something stronger than what you started with. Same with the gold. Copper in silver makes sterling silver. Sterling silver is nice because if anyone has sterling silver, it doesn't tarnish, which is rusting, but for silver. It doesn't turn black. If you have pure silver and you leave it out in the air, it will react with oxygen and it will turn black, which is why you have to polish it. But every time you polish it, you're wearing away some of the silver oxide on the surface. So slowly over the years, your silver jewelry, silver T set, whatever you have, will slowly get thinner and thinner and thinner and be gone because it's been chemically reactive this entire time. Sterling silver is a combination of copper and silver, which is designed to make sure that it doesn't dissolve. It doesn't react. It doesn't tarnish. Why? Because of the mixture of those two helps to protect it. Finally, steel, iron, and carbon. Iron by itself, pretty tough, but when you mix a little carbon in there, it gets so much tougher. And steel is critical. And again, you can make different types of steel. There is such a thing as stainless steel, which of course, again, doesn't rust or tarnish. And again, we use the different words for the same thing. All of these are examples of something unique. These are given a special name because they're so important. Yes, they're all solid-solid solutions, but we usually call them an alloy. An alloy is what we name when we mix two metals together in some way in order to combine them together in some new metal. So metals here like brass and gold for jewelry, sterling silver, steel, bronze, that's a mixture, as I said, of tin and copper, electrum, which is a mixture of gold and silver, pewter, which is a mixture of tin and lead. Pretty sure it's tin and lead. There's a ton of different options, and all of these combine together in order to make alloys, unique combinations, new metals that are incredibly important. Okay, we've got a couple more left, right? There's 9. Liquid solute in a solid solvent. So I'm going to dissolve a liquid into a solid. That one's a weird one, and we only got one example here, dental amalgams, aka dental fillings. Mercury in tin or silver. So mercury, as we hopefully remember, is one of the only liquids on the periodic table. That and, bromine. Now, mercury, if you tried to put that in a filling, well, it would run around. It would be liquid. So instead what they do is they mix it with tin or silver in order to make the filling. Now, there's a couple downsides to this, of course. Mercury is known for being toxic, so hopefully mercury plus the tin-silver amalgam, which is an alloy, technically. Well, no, it's not an alloy because it's not a solid, but hopefully it's safe. Generally, it's been used for thousands of years, so it's pretty good. The question really becomes, why do we use mercury? Why do we use mercury tin? Why don't we use steel? Well, it turns out when you get a filling, you got to fit a very specific requirement. See, I don't know if this is a surprise to you, but bones, while strong, are not stronger than steel. So if you put a steel filling in for one tooth, well, that tooth will hammer down on the other tooth, right? It's like got something like this going on. Whenever you're chewing, you just hammer your two teeth together. Well, if one of the two teeth is a steel filling, it's going to slowly break the other tooth every time it hits it. So when you get a filling, it has to not only be tough enough to handle chewing, it has to be tough enough, not so tough, that it will break the other tooth. Historically, we've used mercury amalgams or silver amalgams, or we've used gold, because again, gold is pretty soft, so we make a gold alloy. Final one here, I think. Is that the final one? No, I think we might have one more. Gas in a solid. A pumice stone, that's a stone that's got air bubbles in it. Pumice actually floats in water because it has so much air in it. Also, hydrogen in palladium. You can suspend hydrogen gas in a palladium, which is one of the elements of the periodic table. It's underneath platinum. You can suspend hydrogen gas in a palladium matrix, making a solution of hydrogen and palladium. All right, 3 more. This should be the last ones. Solid in a gas. That seems like it would be really hard, right? Like solids are generally solid and they don't float, right? They tend to fall because they tend to be heavier than air. So how in the world can I put a solid in a gas? Well, mothballs in air. If you've ever smelled mothballs, the naphthalene, that's a solid particle of the naphthalene molecule floating in the air. It's in a lot of ways, it's almost, you think of it as a suspension, but it's a solution. And the big one, dust in air. Dust in air, right? If there is a sunbeam coming in, and you look in the sunbeam through the window there, and you'll see there's dust floating in the air. That dust is solids. right? It's solid stuff. You know that every time you had to dust your room, which I'm sure you do on a regular basis. The dust will settle on things and it'll make this nice thick coating of white stuff. Dust is a solid. What's it made of? Mostly you. Yeah, dust is usually made of shed human skin, hair, and other things like that, especially in your home. I mean, out in the wild, it's made of other things, but that's generally what dust is made of. It's pieces of you that have fallen off. Maybe that'll get you to dust more often. All right, liquid solute in a gas solvent. So this is a liquid floating around in the air. Gasoline in the air would do this. I think I talked about it with you guys, right? Without the vapor of gasoline floating above the liquid, you can't light it on fire. The liquid itself is too hard to ignite, but the vapor is not. Another one, water in the air. I used that example just a little while ago. That's what humidity is, right? The more humid the environment, the more water there is mixed with the air. But you can't, like, pull the water out. Not easily, anyway. Finally, we've got a gas in a gas. A gas in a gas, well, that's easy. That's the air, right? The air itself is a mixture, a solution of oxygen, carbon dioxide, nitrogen, argon, etc., all mixed into nitrogen. The majority of the atmosphere that we inhale is nitrogen. But nitrogen doesn't do anything for us. It's not a necessary gas for us to live. We breathe it in, we breathe it out. It's just the medium by which the air comes in, the oxygen comes in, and the carbon dioxide leaves. There's one more. Solid in a gas, I forgot one. Smoke. Right? Smoke is solid particles of unburnt material, wood or paper, that are floating in the air. All right, a little note here. A substance is considered soluble, okay, another word here, if it will dissolve in a specific solvent. So if I can dissolve something in something else, it is soluble. All right, so if a solute can dissolve in a solvent, it is soluble. They're not all in the foreign language this time, but they're still all confusing. This is as bad as inter and intramolecular forces. A substance is considered insoluble if it does not dissolve in a specific solvent. Insoluble means it does not dissolve. It is not dissolvable, right? So that's what that means. The in, of course, means not, so it's not soluble. Okay, let's do some examples. 9 types of solutions. I warn you in advance, there will be pictures. You'd think that wouldn't be a warning, but one of the examples involves the inside of a mouth. So some people are a little squeamish about that. I'll try to remember which slide that is, but just so you know, maybe you want to skip ahead. This is kind of the last thing, it's just some examples. So if you want to get started on doing the practice and stuff, you can go ahead right now. But right now, let's take a look what we got. First one, Kool-Aid. What is it? What type of solution are we looking at here? What material is in excess? Which one is the solvent? Which one is the solute? Which one is in the minor power here? Which one is the smaller amount? This is the same idea as the lemonade, right? Oh, there was the teeth. Ah, it came up on screen. This is the same as the lemonade situation, right? This is a solid powder in a solution of water. So this is a solid in a liquid. The next one, here's the teeth again. I missed it already. See, I said I was going to try to warn you, but I didn't. Tooth fillings. So these are tooth fillings in here on the back molars. These are made up of, we said, mercury and silver. And the mercury liquid is in the silver solution, right? It's dissolved in. So it's liquid dissolved in solid. Okay, next one. Carbonated beverage. There's a bunch of different things here. It depends what we want to talk about. We could talk about the fact that we've got carbon dioxide dissolved in the liquid, so that's gas in liquid. But we've also got liquid in liquid because this nice deep caramel brown color is caused by the syrup, the flavoring mixture of the soda pop blended into the water. Smoke. Solid particles floating in a air. This is a solid gas solution. Rubbing alcohol, so called because you're not supposed to drink it, because it's one of the kills you quickly type of alcohols, like pretty much like most of the others, except for one exception. Rubbing alcohol, otherwise known as isopropyl alcohol, is a mixture of alcohol and water. So two liquids. Water is the solvent, alcohol is the solute. Marshmallows. Oh, so yummy. Marshmallows are also a solution. Yeah, I know. Weird, right? Obviously, they're solid. So the main solvent is the solid, because that's why it's mostly a solid. And that's generally something you're going to see, right? The main solvent determines what the state of matter is. So it is mostly a solid. So what's dissolved in it? Well, it's probably going to either be a liquid or a gas. And in this case, it's a gas. There's air as part of the marshmallow. You may remember we did a discussion in the gas unit. We talked about how if you decrease the pressure, the marshmallow expands. That's because the air inside of it will push outward to take up more space. So marshmallows are a confectionery, a cooked dessert of some form, and well, dessert in a lot of cases, made up of gelatin, sugar, and air. The air is what gives it that spongy texture. Without it, it would kind of be gummy, more like a gummy worm, really, because they're made of the same thing, gelatin. Here we've got air. Wonderful, wonderful air. And what is air, of course? It's a gas and a gas, right? We've got the oxygen, carbon dioxide, etc., dissolved in nitrogen. A sterling silver ring, we said this is an alloy, and what we've got here is a mixture of a solid and a solid. We've got copper and silver mixed together. I believe silver is the solvent and copper is the solute, because if it was the other way around, the ring wouldn't look silver, it would probably look coppery. Humidity. Is it humid today or what? There are fish floating in the air. Why? Because there's so much water dissolved in the air. So we've got water, a liquid, dissolved in air, a gas. So it is gas, solvent, water, solute, which is weird. Normally water is the solvent. Obviously, I could flip this around. Air dissolved in water, that's just what the oceans are, right? Water is the solvent, and then air, oxygen, carbon dioxide, and other things are dissolved in the ocean. That's why living things in the ocean can, well, live, right? The plants need the carbon dioxide, and the fish need the oxygen. All right, that's it. Next is solvation process and the heat of solution, but we're going to talk about that next time. So right now, I want you guys to try some of the practice. We sort of went through some of the answers for some of them anyway, and I will see you guys next time.